That's it. Okay. I'm sorry.
Okay. Okay. So, a couple of things. If you want to plan ahead, your big thermo test is going to be this Friday. Okay?
And that means
Telling you.
no homework,
You're
right?
supposed to
Huh?
Wednesday.
Oh, no.
No homework on
yeah.
Friday.
I thought it was
Yeah, homework
Thursday.
on Friday. I thought you were talking about for the whole
No,
week.
I was talking about for Friday.
Oh, no.
So what test are we
We're
having
not gonna have
Saturday
homework
then?
on Friday.
Yeah.
Not funny anymore.
That is
I'm usually a fan of your antics, Colin, but that was too far.
So, here's what we have to get through.
We have a test on Friday, George. That's what you say.
Okay, let's listen, please. Simmer down.
That's funny.
I always listen, Bart.
Let's be respectful.
Let's walk in.
Unless you're talking. It happens. I don't act like it doesn't. So what we've got to get through is finish up this big lecture today, and then we've got a lab on that tomorrow, and then kind of equilibrium on Wednesday, review on Thursday, test on Friday. So that's kind of the sequence. All right. So what we're going to work through. Because if you can kind of understand one of these processes, it'll all kind of make sense later on. So what we're going to start with is a simple idea of melting a piece of ice. Now, this is going to be a horribly boring lab, and this is not going to be the lab that I'm going to do tomorrow. But if I imagine said, all right, here's the story. I'm going to give you a chunk of ice, and you need to make it melt. That's your challenge, okay? So, if you were to do that, what's the first thing that you would have to do?
Put in an environment over 32 degrees.
Or above 0, right?
That's my bad.
Okay? So, here's your chunk of ice. So, but it's something very subtle, what Nathan said, but it's very important. If that temperature is, say, minus 2 degrees Celsius, if that's your ambient temperature, the temperature around that, no matter what you do, you can yell at it, stare at it, coach it, give it words of affirmation, whatever. Okay? Come on, you can do it. Melt. Melt, aggressive. Melt, aggressive. It's not going to do it. Okay? No matter how much you cajole, yell, encourage, you're not going to do it. Okay? But you hit 0. Okay, so here's what's going to be important, is that there is a temperature at which this thing becomes spontaneous. And below which, no matter what you do, it's not going to change anything. Right? You can be at -1, negative 0.5, doesn't matter. There's a specific point where this stuff is going to begin to melt. Now, when you look at what happens in the melting process, okay, so here is my water molecule, okay, hold on, another hydrogen, and these things are held together. And the bonds that hold these together are bonds that hold the water molecules themselves in. These aren't bonds that hold the hydrogen to the oxygen. Those are what we call intramolecular bonds. We break what's called the intermolecular bond. The intermolecular bonds are what hold the water molecules together, not what hold the molecule itself together. Okay, those are much stronger bonds, whole other discussion, not part of the story. So if you're going to go from solid water into liquid water, that energy is going to go into it, and what's going to basically happen on an atomic level is that instead of being locked into the solid lattice, they're still going to be, and this is a horribly non-scientific term, but it's a good visual. They're still sticky, okay? They're still together, but it's a fluid sticky as opposed to a locked-in-place sticky, okay? And again, that is a horribly non-scientific way to describe this, but it's a visual, right? So they're still sticky, but it's a fluid sticky as opposed to locked in place sticky. So that energy has to go to break those bonds. Now, one of the things to talk about is the first law of thermodynamics. First law of thermodynamics basically says, just like matter cannot be created or destroyed, nor can energy. So if you're going to melt ice, that energy has to come from somewhere. So the water is the system, okay, that's your ice, and the air around it is the surroundings, okay? And this is going to be important that you distinguish between the two of these. What is the system and what is the surrounding? So if you focus on what's going to happen to the system, as that melts, right, that stuff begins to turn into a liquid. What's going to happen to the entropy of the ice when it goes from a solid into a liquid? It's going to increase. So from the ice's perspective, we're going to increase entropy, okay? Because you're going from having them locked in place to moving as a liquid. Okay? You're going to increase the number of microstates. You're going to increase the number of places and movements available to these water molecules. But something has to be sacrificed for that. Okay? Something has to be given up. So if you're going to increase that entropy, if you're going to melt those bonds, that energy is going to come from the surrounding. So Mother Nature basically takes energy in the form of photons, and it transfers that energy into the ice, okay? And that's done through random collisions. All right, cool. So the surroundings are going to cool down, all right? As they're going to give up that energy. So the surroundings, they sacrifice their entropy. That decreases the entropy. So let's say it's hot outside, you're going into summer. You're at your graduation party. And you have a bucket of ice for people to use in their drinks. From a thermochemistry standpoint, what's the function of the ice when you put it into the drinks?
Cool the drink. Absorb.
From an entropy standpoint, what are you trying to do to the entropy of the drinks?
Decrease it.
You're trying to decrease the entropy of the drink. Okay? You really want to be cool for the people. I was like, oh, here's your cube of entropic decreasing. Okay? Like, okay? You're cooling it down. Let's go with it. But you're going to decrease the entropy of the ice, or excuse me, of the water. But you're going to increase the entropy of the ice, because what's going to happen to the ice over a period of time? It's going to melt. Okay? So the water's entropy goes down, but the ice's entropy goes up. Okay? So that's the trade-off that you're going to make. So when you look at this, and here's the main point. So when you're melting ice, the delta S for the system, the ice, is going to be a positive value. That's going to increase. The entropy for the surroundings is going to decrease. Now, if you want to figure out what's going to happen to the surroundings, that's based upon, they're kind of two sides of the same coin, which is heat flow and temperature. So you can look at two extremes. If you take an ice cube and you put that outside, oh, the ice cube is going to melt because the energy is going to flow
Into the ice cube. Into the system.
Ladies, please, we're trying to focus.
increase the entropy.
Yeah, she's giving me a demonstration.
Oh, nice. Okay. That's my job.
I apologize.
Okay. So when something is going to happen, the ice melting, is because the ice is at a colder temperature than the surroundings. That's the direction it flows. Now, in contrast to that, let's say you've made a nice cup of hot tea. It's tea time. Aaron, we're making more tea, right? You set your tea outside. What's the tea going to do?
Cool.
It's going to cool down.
Yeah.
So if the tea cools down,
Yeah.
What's happening to the entropy of the tea?
Negative.
It's going down. But what's happening to the entropy of the surroundings? It's going up. Now, if you have a cup of tea that's the exact same temperature as the air,
No, nothing.
what's going to happen?
Equal.
Nothing, right? Because Mother Nature doesn't gain anything. And the bigger that difference is, the more Mother Nature goes, oh, this is bad. Well, I'm going to try and rectify the situation. So when you look at your thermos, okay, what's the function of the thermos?
Something hot.
To decrease the change in entropy.
Yes, to decrease the change in entropy. Okay, so if you have something cold, you want to decrease the increase in entropy, if that makes sense. If you have something that's warm, you want to resist that change in losing that entropy. So the walls of the thermos, the cup, is just a change in entropy barrier, if you think about it. Okay? All right. So here's going to be the main idea. A reaction that is exothermic for the system, okay, blowing up a hydrogen balloon, will increase the surroundings. Okay? Now, that also creates a negative delta H for the system. So think about this. Okay? You all did this. You took copper sulfate. You dissolved it in water. Temperature of the water went up. Okay, great. So that means when you did that, when you dissolved that copper sulfate in the water, the entropy of the water went up because the temperature went up. So you can think of temperature as an indirect way of measuring the amount of entropy in a system. Oh, temperature goes up. I have more entropy. Temperature goes down, that has less entropy. So a negative delta H for the system is a reflection and another way of saying, oh, we're going to increase the entropy of the surroundings. Okay. Now, so this equation is important. It's not on your equation sheet, but it's a huge idea. Now, and I'll tell you why it's so important. It's because of the fact that if you come to me in the lab tomorrow and you go, hey, Burkham, where are the entropy probes?
We don't got one.
We don't have them, okay? Even if you come to me and say, Burkham, we know you have them. You're holding out on us. Where are the entropy probes? I want to start to tell you straight up, you don't have them. So one of the most important aspects of the whole study of science and chemistry in particular is something we can't measure directly. Okay? It's like, wow, that kind of sucks. But look what you can do. You all, and this is why you look at the sequence of things. This is why it was so important that you all did that copper sulfate lab. Oh, you can look at this in terms of delta H. Now, there's a negative sign in front of that for a reason. So, if you look at the units, pay attention to the units. You have delta H, right? So, that delta H is going to be in what units? Kilojoules per mole. Okay? And the temperature, do you think we want to roll in Celsius, or do you want to think we want to roll in Kelvin?
Big K.
Why big K?
Because we don't want negatives.
Yeah, imagine that we want to work in Celsius, like Burkham. I was president of the Celsius Club in high school. I'm all about Celsius. Great. Temperature goes to 0. You put it in an ice bath.
Undefined.
Okay, it's undefined. Okay? Worse yet, you have a -5, which gets even weirder. Okay?
Oh, no.
So this temperature has to be in Kelvin. So typically, if you look at this in terms of delta S, there's a negative sign out there in front of that. That'll make sense in just a second. So typically, delta S values are pretty small. So typically, enthalpy or entropy changes are joules per mole Kelvin. Now, here's the reason why we have this negative sign. If you look at this equation, it says delta S for the surroundings is equal to negative delta H over T. So this is for the surroundings. This is for the surroundings. Okay? So let's say that you have an exothermic reaction. Okay? Run at a particular temperature. So if you have an exothermic reaction, this is the logic of this equation. If you have an exothermic reaction, what's the sign of delta H? Negative. So if you have an exothermic reaction, you have a negative delta H over some temperature in Kelvin, right? So an exothermic reaction means that energy is going to be given off. So what's going to happen to the entropy of the surroundings? It's going to go up. So this is why basically it's a negative of a negative. So if you have an exothermic reaction, heat's given off, great, but the entropy of the surroundings is going to go up. So you all have measured enthalpy changes. You measured, what happened to the temperature of the water. You divided that by the moles of the copper sulfate. You all have calculated delta H. Huge experimental errors, but God bless you for trying. You tried, okay? You calculated delta H. Then you decide, what temperature did we run it at? Okay, we ran it at 20 degrees Celsius, 293 Kelvin. We divide that by the temperature. Boom. That's how you get your delta S for the surroundings. Now, if it's in the other side of this, Opie,
Is that like KT per what? That's circled right there?
joules per mole Kelvin.
This temperature?
This temperature is just in Kelvin. Okay.
Okay.
Now, if it's an endothermic reaction, what, Skippy?
If we all open our doors, right, and we let the AC out, can we prevent global warming?
Oh my God, no.
Okay. No, because AC
No. That's just a train wreck. That's being.
I'm trying to solve
It's going to make it
global warming.
worse. It's going to make it worse.
We'll
We'll talk more about that. So, if it's an endothermic reaction, what's the sign of delta H?
Positive.
Positive. But then you have the negative sign in front of it, because if it's an endothermic reaction, what's it doing? Cooling down. So the entropy of the surroundings is going to go down. So that's why this works. That's why that negative sign out front isn't just some, let's just randomly throw a negative sign out front. What's a negative sign between friends? That's the important part of that. Okay.
So,
Yes.
just to confirm.
Just to confirm.
So the delta H is still like the delta H we get of the system.
Yes.
But then the negative makes it so that it's of the surrounding.
Yes.
So we shouldn't change it before putting it into this equation.
No. Do not change it. Do not change it. Do not change it. Do not change it. Do not change it until you put it into this equation. Isaac Briggs.
A little bit unrelated, but is the reason why we don't have these probes because we don't have enough money, or they actually?
No, Israel's not straight to technology.
Okay, I wasn't asking you. Do they actually not exist?
No.
So scientists actually have to do this. I thought it was just us. I thought it was just like the beginning, Yeah, beginner level.
Yeah. If once you made it to AP Physics 2
Oh yeah.
or AP Chemistry 2,
Yeah.
we have them.
Okay.
I'm just being a jerk. No, they.
Wait, yeah, you're just. Have you ever? Is there an AP Chem?
No.
Well, I know we don't have it, but like.
But no, there is.
Not yet.
Not yet. Okay. Good with this. Yeah, they just don't exist. Okay. No, it's cool. Okay. Now, so the first law of thermodynamics, and this is how Einstein's equation relates to this. E equals mc squared. So, common misconception about this. M is the change in mass. So, for example, very, very short version of a long lecture. Right now in our sun, 4 hydrogen atoms, not that sun, but our sun, that sun, is changing into helium. Okay? So a hydrogen atom is basically 4 protons. You have 4 St. Bernards. That turns into helium, which is 2 St. Bernards. and 2 sheepdogs. So if you take the mass of the 4 St. Bernards, the 4 hydrogen atoms, and you compare that to the mass of the helium atom, there's a very, 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 very small loss of mass between the two of them. And that difference of mass is what gets converted into energy from Einstein's equation. It is not the mass of the hydrogen, it is not the mass of the helium. It is the difference in the mass between the two of them. Okay? Now, it doesn't take much mass to make a huge amount of energy. So if you consider the speed of light as 3.0 times 10 to the 8th meters per second, and then you're going to square that, right away, that gets you 9 times 10 to the 16th. Okay? That's a big number. So it doesn't take very, very much loss of mass in between those two, which is incredibly small. But since you're multiplying it by 9 times 10 to the 16th, it doesn't take much. Okay, so right now in our sun, I don't remember the exact numbers right offhand, but every second about 200 million tons of hydrogen is converted into helium. Okay, don't flip out and go, oh, that's a lot. Okay, our sun has been burning for about 5 billion years. We got about another 5 billion years to go. Give or take 10 minutes. We'll be okay. Okay, we're going to screw this thing up before that happens. Yes?
I heard they actually changed equals MC squared to be equals MC squared plus AI. Is that true?
I get it.
He gets it.
I don't get it.
You know what this face indicates?
It's a good joke, right?
Yeah, it's funny.
No.
I think you should tell him another joke.
Yeah, no, I think it's a joke too.
Isaac, the answer Darth Maul.
No. By the way, speaking of which, if y'all want to do an AP chemistry short, which we haven't done for quite a while, we last Thursday night when we had the study session. By the way, for those of you that are taking the test, I posted the reviews up there, and those sheets are over there. For those of you that are taking the test that didn't make it to the review, you can watch the YouTube videos now. And so we had some various ideas for the AP chemistry short. So if that's something that collectively you all want to decide that you want to do, then that discussion needs to happen at some point, like what you want on it, what color you want on it, what you want on the design, that type of thing.
We still have
We just went
Huh?
small.
We still have
Tomorrow night.
Or what's even better is.
Yeah. Okay.
Oh, I see that.
So
You done?
Oh my, okay, most of the time it's not half of the class.
Whoa.
today it has been this half of the class.
Hey,
Okay.
Hey, but it's-
I'm telling you.
It's never the middle.
Oh, it's never the middle. Well, except for maybe sometimes the middle back. Okay.
But not the middle
Not the
middle.
middle. No, not the middle. Okay. Now, the beauty of what Einstein did is that if you look at the units,
Like you're really alive.
it had to be MC squared, because that's the only way you can get joules. It couldn't be MC cubed. It couldn't be MC, because if he just said, oh, E equals MC, well, MC is just momentum, because that's just mass times velocity. So it couldn't have been cubed, it could have been squared, it had to be squared.
It was kind of a cornball, like you just play that one.
Well, what he got lucky on is that there was nothing in front of it. There's no pi, there's no 1/2, there's no square root of 9, okay? And that's actually a shortened version of a much longer equation, but that's just the short version of it. Okay, now, here's the second law, not suggestion, law. That says any spontaneous reaction, there is always, not sometimes, okay, not most of the time, not 90% of the time, always an increase in the entropy of the universe. And when I say in the universe, I mean the universe. I'm not talking my room, I'm talking the universe, Big Mike.
How do we get that number?
How do we
What's
get
the
what?
speed that like? How did we get the speed?
They timed it.
We'll talk about that in AP physics. Okay? They literally did time it, but they had to have rotating mirrors and shoot it over the wall.
It's kind of cool.
James Clerk Maxwell actually predicted the speed of light before they actually calculated it. So that's another idea.
Was he close?
Okay, so delta S of the universe, okay? I mean the universe is the sum of the change in entropy of the system plus the surroundings. Now, for this to work, delta S of the universe could be three possible values. It could be a positive number. That means the reaction is spontaneous, okay? And so literally, so like if you see it, we'll go through the math later on. If you look at the calculation of the increased entropy of the universe for ice melting, it is literally a positive number. Like the entropy of the universe is increasing. For a non-spontaneous reaction, delta S of the universe is negative. Okay? So here's another set of criteria that you need to know hardcore. So E naught, positive or negative for a spontaneous reaction? Positive. Delta G, negative. K values, big or small?
Big.
So big K, negative delta G, positive E naught. To that list, you need to add delta S of the universe as a positive number, indicates a spontaneous reaction. So the other option is that delta S of the universe just might be 0. But all that means is that you're just in equilibrium. So if you look at this equation up here, delta S of the universe, so here's the ramifications of this, is that the only way this can happen, for example, let's say that you have the surroundings as a positive delta S, okay? And these always have to have opposite signs, right? Because if the surroundings are going to increase in entropy, it's because the ice melted and the delta S for the system is going down. So the only way this can happen is if one of those values is bigger than the other one, okay? Especially if it's going to be a spontaneous reaction. If it's not, then it's a negative value. So if you look at minus 5 degrees Celsius, whatever the sign of delta S of the universe is, it could be 0, it could be negative, but it's not a positive value. So here's the ramifications of this. And this will make sense in just a second. So no process that produces a lower entropy in a system can proceed without producing an equal or greater amount of disorder in its surroundings. So the second block, you really can't tell it, but I did some tidying up around the back of the room. Okay, put away some cords, set up the next lab. Okay, kind of tidied up my desk a little bit. I decreased the entropy of the room. Okay, not a huge amount, but I did some. So if you consider this to be the system, and the room cleaning itself is not a spontaneous reaction. I wish it was. It's not. Okay, not a spontaneous reaction. So in doing that, I've increased the entropy of the room. Okay, because of the fact that I moved through the room, my body was giving off thermal energy. Okay, I was disturbing the particles of air that are inside the room. So by me moving through the room, I increased the entropy of the surroundings, if you consider that to be everything inside the room. But the system, which is the stuff, okay, that saw a decrease in entropy, but I increased the entropy of the room by moving through it. So mom and dad say, hey, you need to clean your room. Basically what they're telling you, what do you need to do to the entropy of your room? They're saying decrease the entropy of your room. Right? But, and you need to say that, hey, mom, dad, great, I'll do it. But you just need to know, I'm going to also increase the entropy of the system of the house and the air and everything in it. Just so you're aware. Okay? Nothing is free. I'm just telling you. Oh, there you go. We don't care. Clean your room. Got it, Mom. Okay. So, you look at this. A nail rust. Okay? So here's the technical formal equation for rusting a nail. 4 atoms of iron react with 3 oxygen molecules and you produce Fe2O3. Okay? So one of the key things that you need to be able to look at, and gases are a cheap and easy way to kind of figure out what's happening to the entropy. So one thing you can look at is that you have 3 moles of gas, and gases, remember, have a tremendously high amount of disorder, tremendously high amount of entropy. Because they're like fast guys going, rah! Okay, bouncing around. So you went from having 3 moles of gas with a very, very high entropy, and now they're bound up. It's like, oh, dude. Okay. Yeah. So if all you saw was this, and you're going from 3 moles of gaseous reactant to 0, you got to figure the entropy for the system is going to drop dramatically because you went from having these free oxygen molecules bouncing around to them being locked up in the structure with the iron. It's like, oh man, the oxygen molecule sucks. I was like, man, I was living the good life. I was bouncing around, moving and grooving. I'm stuck on a rusty nail giving somebody tetanus when they stuck on it. Cool. That's
Well, tetanus doesn't come from the rust itself.
I know, but that's what everybody.
Oh,
That's,
Nathan, do you mind?
No, because I cut myself this week and I thought I had tetanus. I did use it.
did you go get a tetanus booster?
Hopefully within the last 10 years I have one. I don't know if I did.
Wait, what is it?
Huh? It's the bacteria. Bacteria.
It's
is a
usually
virus.
because
Yes,
the
bacteria.
bacteria's in like the soil.
Yeah.
And so rusty nails are usually.
Yeah, bacteria. Okay. Now, so let me Mara, stop that. I need to hand out some guided lecture notes.